So today I'm going to talk about Topo-Bathymetric Lidar surveys for in rivers and how we can use these data to improve fish habitat and fish passage. So I want to acknowledge some of the other folks at AGRG, which is part of the Nova Scotia Community College. We're a spin-off out of COGS back, hard to believe, about 24 years ago now, back in 2000. Nathan Kroll, Thomas Allen, Kevin McGuigan, Kevin Ferris, and Lauren Douglas, among a few others, have worked on these different data sets I'm going to be showing you today. First, let's take a step into the Topo LiDAR world. And just a quick recap on all the great things we can do with topographic LiDAR related to hydrology. We can use the D8 algorithm on a high-resolution DEM to come up with things like flow direction, flow accumulation, and from that derive a synthetic stream network. From there, we can derive things like stream order, where we have single streams going into each other, becomes a stream order 2, and as these accumulate, we get higher order streams. We can do things like calculate the slope of the longitudinal profile, and in this slide it's a little bit small, but you'll see we have some very steep sloping areas in red in the middle slide here, and then other things like looking at the riparian zone using the digital surface model to see where we have shade or exposed river area and so forth. And of course this affects the thermal regime. It's been our experience here in Nova Scotia that the LiDAR-derived stream network is typically more accurate than the hydrographic network that is in the GIS data sets that are provided by the province. And most of this relates around trying to derive the streams from photogrammetry under the forest canopy, which is quite challenging and so forth, whereas the LiDAR streams are all derived by elevation. Okay, I'll talk a little bit about the Chiroptera. NSCC, we own a Leica Chiroptera 4X system. It uses a near-infrared laser firing at about 500 kilohertz and a green laser firing at about 35 kilohertz. It's a 515 nanometer, as well as we have a 60 megapixel camera, RGB and near IR there. A couple of things here. On the top right, we're showing the scan angle. So it scans at about 20 degrees side to side and 14 degrees forward and aft. This is bottom is our screen showing the actual what the operator sees, and we can see this small spike here on the other side of the large peak on the histogram, and that's showing we're getting good bathymetric returns. If we jump to the top left, this is the typical waveform that's captured by the green laser. We get a strong reflection off the sea surface, and then depending on the water clarity, we have variations in the water backscatter part of the curve, and then ideally another peak at the seabed, and perhaps if there's material or other objects, we may have two peaks here. We use these peaks obviously to record the range, the timing. It's real important we know where the water surface is because the speed of light reduces significantly from air to water, and with that change in the speed, we also have a refraction angle we need to account for. We also record the amplitude so we can get LiDAR intensity of the seabed. These last two shots are just a couple of the installs showing, in this case, the hood is off the LiDAR, showing the two green lasers, and that's the IMU sitting up top there. So, what can we do with Topo-bathy LiDAR for rivers? Well, one of the quick derivatives is to get water depth at the time of flight. So I just mentioned we map the water surface as well, penetrate to the riverbed. From there, we can subtract those two and get a depth map. From that helps us figure out where's the thaw wig. This is the deeper part that streams naturally make as they meander side to side. We can also use that data to derive the longitudinal profile. On the top right here, this is the longitudinal profile of the main stem of the river. Shows us the gradient, if there's pools, if there's riffles where these may affect fish habitat. So we can also take a look at bed forms. and make use of these data for flow models, where in the middle graph on the bottom here, we show that discharge is related to the cross-sectional area of the stream and the velocity. And obviously, depending on that bed form on the bottom, we can have more resistance to flow. And I think this is going to actually, it's starting to already revolutionize flood modeling for rivers. In the United States, USGS is going full bore on this type of data collection. We're starting to see it more and more in Canada. Quebec seems to be the leader in terms of putting out contracts for river surveys. So it's well suited for hydrodynamic modeling, looking at flooding, things like this, but also we can use those hydrodynamic models to look at fish passage where we may have low flow or high flow conditions. And I'm going to talk a little bit today about how we can integrate these data with drone information such as thermal imagery. First, I thought I'd give you a quick cross-section, point cloud here. We could see the forest canopy here. We have some low dense shrubs. We have the ground, and then finally we have the riverbed bathymetry, and then the water surface itself. We have both a measured water surface and a derived water surface here in ground. These other pink points below the ground would be categorized as noise. Essentially, this would be a multipath effect of the LiDAR, where it then effectively gets projected under the ground. The points don't make it under the ground, but simply project it. Okay. So again, traditionally we've used Topo LiDAR on the left-hand side here and the D8 algorithm or the D infinity algorithm to come up with the stream network. What we're finding with the Topo-Bathy LiDAR, and here's an example of the water surface and the terrain, and then the bathymetry underneath, we subtract and we actually get our depth. So we can see these shallow spots here at the just before we come and make this meander and the deeper thalweg. We're using the least cost approach in order to trace the path of the river itself using the inverse of the depth. So 1 over depth, and we give a start point and an end point, and the least cost algorithm figures out the best path for us. And the nice thing about that, it essentially goes from pool to pool. So that has some implications that I'll talk about in a moment, but let's just have a quick look here at the orthophoto, and we can see these deep pools that are measured by the LiDAR. And as I mentioned over on the right here, we're just looking at how we can use that to improve our cross sections for in this case, a 1D model looking at both flood depth and flood velocity or flow velocity. Here's an example of the cost surface on the left integrated in with an orthophoto, and this white line here essentially is the right result of the least cost surface. Remember, this is 1 over depth. So it's trying to go to the least cost, so the least effort to move through. So you'll see it preferentially goes into these blue areas. When we conversely look at the depth, that means essentially we're going from pool to pool in a very linear fashion. I'm going to show you an example in a minute here of what the Topo river would look, Topo-derived LiDAR river would look like, and how it has some implications that I think this approach fixes. And we just see it over the bathymeter or over the orthophoto, and we can see some riffle marks there. So here's an example on the left of using the D8 algorithm on topographic LiDAR. And you'll notice that the line really jumps back and forth quite frequently. This is a common problem with topographic LiDAR-derived water surfaces. You often have specular reflection. The water surface typically isn't represents the proper gradient of the river and so forth. On the right-hand side, the line is much straighter, much cleaner, fewer jigs and jags back and forth. What are the implications of that? Well, the implications are we get an artificially too long of river when we're using the D8 algorithm on Topo LiDAR. This is something researchers need to be aware of. For example, if we were to plot this longitudinal profile for the river, we get about a 17-kilometer long stretch. Whereas if we compare the D8 algorithm using the least cost algorithm, my apologies, using the Bathy LiDAR, we get a river length of about 13 kilometers, okay? the data is accurate to within 15 centimeters. It's the same spec underwater as well. Here's an example of a cross section where our GPS points are in white and our classified bathymetry points are colored brown for the ground, blue for water, and then shrubbery in the green here. And we can then look at that at the gridded DEM scale, and we see we have a mean offset of about 9 centimeters, a standard deviation of 8. And yeah, we'll do anything in order to pick up those points and really be sure we've got them. That's yours truly having a little dip, collecting some of those deeper cross-section points. Good job. I'm as tall as I am. We'll have to start sending the tall people for deeper surveys. I'm going to jump now to a place called Middle River up in Cape Breton. It drains into the beautiful Bedore Lakes, and this shows the entire watershed. We surveyed mainly along the stem of the main river. This is a hydrograph showing the river system is gauged, and we want to try to fly at low flow conditions, ideally avoiding these large discharge events. When we have rain events, the water tends to get more turbid, more stirred up. So we really want to try to hit it either at low base flow or once the system is settled down after a rain event. This shows the swath that was covered with the Topo-Bathy Lidar in white. And again, one of the benefits of the longitudinal profile is, in this case, the water surface is shown in red, and the actual bathymetry is shown in blue here, or the riverbed. And we can see that basically we can also identify waterfalls, deep pools, etc. So again, the steps are water surface, seamless DEM. We subtract those two, we get a depth map. From that, we do an inversion of the depth map. We do the least cost. We convert that line into a series of points, and then get our longitudinal profile. I'm going to talk a little bit about how we can raise and lower that red line, that water surface, and to do that, we're using a hydrodynamic model. Okay. I'm probably going to skip this slide. There's way too much text here, but basically it's talking about that on this particular survey, we had our near-infrared laser failed, which really is what we depend on to give us the precise water surface. So what we've ended up using is we've done some simulations in the hydrodynamics using the riverbed in order to simulate the water at the time of flight, and from that we've used that to correct our bathymetry and that change in the speed as I mentioned. And essentially, once we've corrected the data, we see we've got a mean of about 7 centimeters, a standard deviation of 9, and that's quite an improvement before we did the speed correction. So here is an example of the bathymetry in brown is before the correction for the speed of light change through the water versus black being the corrected surface. And the blue is the water surface itself. So you can see this river has many steps, many little mini waterfalls. Now, you always want to know how real is that? Is that really correct? Down below, we have essentially the depth profile at both the time of flight and then at low flow conditions and at high flow conditions. They're basically the very similar shapes, just amplified or reduced. Let's have a look at this particular area here and see if what we observe in the field matches this. So this would be, you see this sort of linear feature in the river where we go from essentially a step. Location of the riffle. And if we look over here on the photograph, we can see that on one side, Lauren is about knee deep over here compared to on this side. So there definitely is a distinct step in the water surface as we move from this bouldered area into this faster flowing area. So in fact, we feel this is an accurate representation of the water surface, and as a result then of the bathymetry. And as I mentioned, we can use the hydrodynamics to do a high flow discharge versus a low flow. In this case, we have the longitudinal profile running through the high flow discharge, so these are fairly deep areas. And in contrast, we can reduce the flow and look at the low flow conditions, and then we can start to spot where we may have trouble with the fish passage, trying to make their way up in these very shallow areas. So this can help people that are out there looking at river restoration, where perhaps they may need to do some kind of work to deepen the channel in these areas. A little bit, let's look at here's a seamless Topo-bathy area. There's the river channel. There's the depth draped over the orthophoto. And now we've been starting to fly the DJI M300 with the HT20 sensor on it. And that's what's shown over here on this rocky shoreline. And if we just query some of these points, we see most of the water is 17 to 16 degrees, but we do have some cold pools entering at about 12 degrees. And I'm just going to take you now and look, zoom in on this particular area, and also to talk about how complicated the drainage is. This is the orthophoto we captured at the time, so you can see the main stem of the river over on the left side, but you can see also these old meander scars where some water is still making its way through some of these old meander scars. When we look at that in the elevation, the bare earth model, we can certainly track those meander channels as well as the main stem. And what also caught our eye were these hole-like features. And what these turned out to be are actually sinkholes. The geology in this part of Cape Breton is underlying by evaporate rocks. So these would be gypsum, limestone, perhaps salt an area, but dominantly gypsum. And this is what causes the karst topography, where groundwater essentially dissolves the rocks. You get caverns, you get sinkholes. And in fact, one thing we were curious about is, does this type of geology actually act as a plumbing system to help promote springs seeping into the water column, into the river channel here? And as you can tell, looking at the aerial photograph, it's pretty tough to see any of those sinkholes. This is our area again where we're looking at. Here is our depth at the time of flight, so we can see these pools, and the LiDAR or the longitudinal profile is preferentially going through those as mentioned. And now we start to pick up these sinkholes along this side of the this higher plateau. Now, what we then did was we looked at the thermal data, and we flew a strip from the bridge down several kilometers, maintaining our line of sight and following all the rules of UAVs and so forth. And essentially what we're seeing here is about a 2-degree variance in our thermal regime, from warm up at the bridge where it's exposed and open, not much shelter. But here, this 2-degree area seems to line up when we get close to this cliff area where we have our sinkholes. So we think, in fact, that indeed the karst topography is acting like a plumbing system and allowing that cold spring-fed water to enter into the stream. Now, that has important implications for refuge areas for fish during the peak of summer months when flows are low and the water temperature can heat up. So the combination of the bathymetry and the thermal data really provides us a rich environment to look at the relationship of both fish habitat, fish passage at varying flows, and then of course the thermal regime where we may have refugia for fish to be able to survive during the hot summer months. Again, just looking at the least cost. So to summarize this little talk, the Airborne Lidar was paired with the HT20 sensor. This is an RTK unit. We were able to pick up radio signal there, so the positioning was quite good with the RTK system. And we've worked out how we can make use of that data in order to geocode these thermal images. Initially, the data does not come out from this particular sensor, does not come out directly as a degrees Celsius value, but we dug in and found some code from DJI that wasn't fully released with the sensor, where we can convert the data into degrees Celsius values. The water depth is a very useful metric, and we use that to calculate this least cost to get the main river stem. And we feel this is a more accurate representation of the true length of the river for the longitudinal profile compared to the traditional method of using the D8 approach on Topo Lidar, which always produces too long a profile. I mentioned the DJI software made it somewhat limiting to get the degrees Celsius out, but we were able to eventually find a way past that. And we just have a new Ultim sensor, multispectral sensor. This was from the folks who made the Mica Sense. It's got blue, green, red, near-infrared edge, near-infrared, a detailed panchromatic band, and a thermal band that produces data in degrees Kelvin. So for most of us, we'll want to shift that to degrees Celsius, but that's a new sensor we're very anxious to get out and start using this coming field season. The deep pools and cold water really are sort of the key habitat, key areas to look for fish survival in the summer. And we think, in fact, that the karst topography is a conduit for some of these spring-fed rivers. And I think our hypothesis is looking like it's working out here based on, again, a fairly limited number of surveys, but based on what we're seeing here. So that concludes my talk, and I'm happy to have a discussion, and I'll just look in the chat here. There's a couple of questions. How does the system work in salt and fresh, salt water versus fresh water, warm versus cold water? And many of you who are familiar with echo sounding, multi-beam or single-beam echo sounding, realize that the speed of sound varies quite dramatically from salt to fresh, and likewise from warm to cold water. Thus, we have to continually do drops to measure those parameters to understand if we have a thermocline or a halocline. In the case of the Topo-Bathy Lidar, the variance in the speed of light between fresh and salt and warm and cold is very minimal. So it makes it an ideal tool to be able to survey estuarine environments where you're moving from a saltwater environment up through a freshwater environment. Next question I see here, what is the maximum depth you can measure? Well, in rivers, we've gotten to probably about 5 meters at the maximum. There are a few rivers where we lose the signal, and speaking with people in the fish habitat world, and they say, well, you know, that's a useful metric to be able to at least say for those areas, it's at least 5 meters or greater than 5 meters. Out in the ocean, on the coast, for example, on the Atlantic shore, we've gotten to probably 15 to 18 meters. On the Northumberland Strait, I think our record there is at about 12 meters. So the depth of penetration relies really on two factors. One is the clarity of the water. So for example, non-turbid conditions are ideal. And also something here in Nova Scotia that is a problem for our southern rivers, a high degree of tannins. So the water is extremely dark. So tannins and dissolved organic carbon, DOC, has a tendency to be a light trap. And unfortunately, in those rivers, this technology is not very useful. And then, of course, if you have a river that normally runs clean and then after a rain event, perhaps it's stirred up and brown and more turbid, these are where you really have to monitor the conditions and wait for the river to calm down again. Who is using these? And the other factor, let me just finish this other one before I read this next question. The other factor that influences depth of penetration is the reflectivity of the bottom. Probably not such a concern in rivers, but definitely in a coastal environment or a lake environment, the more reflective the bottom, the deeper you'll penetrate. Who is using this data in government and for what? In terms of river surveys, the federal government is starting to put out contracts for flood risk mapping using the rivers because we get the cross sections. We can get as many cross sections as we want, and these are very costly, sometimes dangerous and expensive to acquire. As I mentioned, the Quebec government is using it, probably has put more RFPs out there than anyone. I would say the main driver right now is flood mapping. However, the old idea in geomatics of collect it once, use it for many things, fish habitat, fish passage is an obvious choice. Can you comment on when you think the cost of bathy will be lower towards the cost of a topo lidar? Well, I think it is coming down. Part of the rationale is that often we'll fly lidar with a twin engine aircraft. This is especially true for coastal surveys where we need to go further offshore or perhaps go to islands. There is some advances in bathymetric drone technology, but the challenge with bathymetry is that we need to build up more power in the green laser in order to punch through the water column. It's still an eye-safe system, but it is somewhat challenging from a power consumption. Another question here, does it make any difference with the direction of flight, and do you also try to incorporate any flight lines that cross the stream direction, upstream versus downstream? No, you're basically flying at, for example, that data collect there probably took us maybe 3 hours. So you don't really notice any difference with flying upstream or downstream. And in fact, our flight lines would have been upstream, make our turn, downstream, upstream, downstream. The fact that this laser system, I should also mention, where we have a lot of air bubbles, this would be either in the surf zone on the ocean or say after a waterfall. Those air bubbles are problematic to the laser and often will attenuate the signal and we don't get good penetration. So this is where this elliptical scan pattern is very useful, where we get to survey the area twice, once on the forward, once on the forward and back scan. So sometimes we can get lucky and that bubbles and foam will have moved. In other cases, are you hiring at AGRG, and if so, for what? Yes, we're always looking for summer positions. We're going to be hiring some students coming up. We have several research projects on the go that are looking at that, and then that's a great ground to sort of test things out to see who we think is a good fit for the team for a longer type of duration.